Hi students, hope you are doing well. Today we start one more Fortran lecture, a tutorial, and today we are going to talk about the Simpson's rule, which is a method for numerical integration. I'm Dr. Ganguly. Now of course you know that when we want to find the integral of some function, for example fx, and this is a definite integral between the bounds a and b, then we actually need to find the shaded region which I have shown here. So you have the function f of x and you have these two bounds here, say x is a and x is b, and this shaded region represents the value which is also given by this integral. So there are many people who have come up with different methods about how to find this shaded region. So let's look at that here. Now the method we discussed in the previous lecture was the trapezoidal rule. And in the trapezoidal rule, what you do is that you consider this region to be made up of a set of trapezoids or trapeziums. So essentially you can see here that if I were to connect this two lines here, lines in red, with a straight line, then I would essentially have a trapezium here. I would have a trapezium here and so on. And if we sum the cross sections of all these trapeziums, then we would essentially get the integral value. Now what is done in the Simpson's rule is that you consider this to be a quadratic variation. So through that you come up with this formula here. Now I'm not going to derive this formula because the aim of this lecture is to come up with a code to implement this formula, but you can find many tutorials out there, many sources or many resources on the internet itself. If you search Google, and you will also find this given in many textbooks on numerical methods, numerical analysis. So the Simpson's rule is given as a to b integral fx dx. This particular definite integral is approximately equal to h by 3 fx0 plus 4 fx1 plus 2 fx2 plus 4 fx3 plus 2 fx4 and all the way to 2 fx n minus 2 plus 4 fx n minus 1 plus fxn. Now, if you look at this series, you will see there are some commonalities here. For example, the fx0 and fxn, they only have a coefficient of 1, but then you have fx1, fx3, and all the way to fx n minus 1, they have a coefficient of 4, and then you have fx2, fx4, all the way to fx n minus 2, these have a coefficient of 2. So we can come up with some expression for this series, and hopefully that will help us in writing a Fortran program to implement the Simpson's method or Simpson's rule. So let us now work on that formula. So I have again written out the formula here in larger font, and then what I have done is I have brought certain terms together. So for example, we have the fx0 and fxn here, the first and the last terms. Then I have brought in all the terms which involve the coefficient 4 here. So here I have fx1, I have fx3, you can see here, and also there will be fx5 and so on. And I will finally have fxn minus 1 from this here. Now the next thing is all the terms which involve 2. So again I have 2 here, and then I have fx2, I have fx4, and again I have all the terms here, for example fx6 also, and then the final term would be fx n minus 2. Now if we look at this summation here, what we are going to see is that there are these terms in red which have coefficient of 4, and there are these terms in brown which have a coefficient of 2. Now if you look at this closely, you will realize that n should be an even number. So for example, here x1 is odd, x3, I mean the coefficient 1, 3, 5, these are all odd numbers. So if I continue like that, then n has to be an even number for n minus 1 to be an odd number. So for example, if I was to take n is 2, then this would be x1, and if I was to take n is 4, then this would be x3. So essentially n needs to be an even number. You can see that from this also, that n minus 2 should be an even number Therefore, n minus 2 would be 2, which would mean that is of course a trivial case here, but so on. You will get many different terms. So essentially, we can now look at this and we can try to write it in terms of a summation. So that's what I've done here. I have taken the two green terms. These are x0 and xn terms. And then all the terms involving the coefficient 4, we can bring the 4 out. And then this is going to be f2x 2k minus 1, k is 1 to n by 2. And again, I have the term here, the coefficient 2 is brought out here, and then I have this summation term here. So now I have a formula which is more easy to implement as far as computer programming is concerned. Of course, I will need to calculate these two sums using some kind of do loop. Let us try to get some more insights into this formula. So we can again write the formula here, and of course you realize that x0 is a and xn is b. These are the two ends as far as the integral is concerned. And then I can of course write x1 is a plus h, x2 is a plus 2h, xk is a plus kh, and so on. So remember here that this region between b and a has been partitioned into n subregions, and therefore each of these regions has the length h. Like I mentioned before, this is very much like what we do in trapezoidal rule. So now with this general formula here, xk is a plus kh, I can write some general terms. For example, I can write x2k minus 1 in this form here. So I have replaced the k here by 2k minus 1. Similarly, I can write the x2k term as a plus 2kh. Now, what all this is going to help me do is that I can now write this I value in terms of a and b. So that's what we do in the slide here. I have again written out the Simpson's rule, and then using the fact that x0, xn can be written as a and b, and x2k minus 1, x2k can be written in terms of a, k, and h, I can come up with this formula here. Now remember, there is always the link between h, b, a, and n. So some people like to use the formula in terms of h, some people like to use it in terms of a, b, and n. Your mileage may vary. So again, finally, we get this expression here. So now this is the expression with which we are going to work in the future slides. Let us continue this process, and before I move forward, let us try to get some concrete values in terms of the Simpson's rule, and let us put n is 2 to get a certain formula here. Now if I put n is 2, what's going to happen is that I take that expression for Simpson's rule and I put n is 2 here. So for example, 3n becomes 6 and the 3n becomes 6 in different places also. So this is what I get here. Now one thing you can clearly see is that the summation here is going to be from k is 1 to 1 here, and k is 1 to 0. So as far as this particular summation is concerned, the one with coefficient 2, this is simply not going to come in when I consider n is 2. So I am left with only this part of the I value. So I get I is this value here. So FA, FB, and then I only get 4F, A plus B minus A by 2. Now remember, I am going from k is 1 to 1. So k is simply 1. So if I put 2 into 1 minus 1, I get B minus A by 2. Now I do some further simplification of this part here, and I continue to simplify it. So I get A plus B by 2 here. Now, through some math which I have shown in red here, you can see that h is b minus a by n. So that will be b minus a by 2 given n is 2. I could write b minus a is 2h from this formula here. And I then get b is a plus 2h. So I can write a plus b by 2 as a plus 2h by 2 or a plus b. So essentially what happens is that a plus b by 2 can be written as a plus h, and so I can write this formula in green here. Now many people call this the Simpson's 1/3 rule because you can see here h by 3 is present, so the 3 being here, this is called as the 1/3 rule. So now of course we need some numerical example to check out this method, so we use the expression we have used previously in the trapezoidal rule. So this integral was 0 to pi by 2 cos x by 4 plus sin x into 1 plus sin x. And in question bank 6, in tutorial 6, question 6, I have calculated this integral as this value here, and this value comes to 0.156667 if you want to get a numerical value for this. Now, of course, if you want to check out this integral, it's quite easy to solve. You can, for example, set 1 plus sin x equal to t and then substitute and then work forward with that. So again, we know this exact value, so this is a good way to compare the numerical method. First, let's try it out with n is 2, the Simpson's rule. And so we do that. Again, we know a is 0, b is pi by 2 in this case, and I can use the expression I derived before for the Simpson's 1/3 rule, and I simply substitute f0, f pi by 2, and f here a plus h, and I will get the value. So again, remember that a plus h could be written in this form here. So remember that h comes out to be pi by 4 because b is pi by 2, a is 0, and n is 2 here. So I have all these values now. Let us calculate it in the next slide. So that's what I have done here. I have taken the value of f of x, and I can immediately see f0 will be simply 1 by 4, and f pi by 2 will be 0. Remember, cos 0 is 1, and of course you know cos pi by 2 is 0, so this becomes 0 here, and I can find f pi by 4 and I get these values here. Remember, pi by 4 would be 180 by 4, that is 45 degrees. So corresponding to that, I have the values of cos and sine. I get these numbers here. I get 0.087997 and so on. So I substitute all these numbers and I get this value of I, which comes out to be 0.1576, pretty close to the actual exact solution. Now I'm going to use some of these numbers here which I've shown in red to check out the computer program. So let's write the computer program. Let's write the main program first. So I define pi as a cos -1. So remember, you can of course use pi as 3.14159, but I do not always remember all the digits. So you can use arc cos here, and that's going to give me the value of pi. A is 0, b is pi by 2, n is 2, and I get the exact solution here. Remember, the exact solution for this integral is 1/3 3 log 2 minus log 5. So in Fortran, the natural log is given as a log. So I have that here. And then I will simply calculate the numerical integral value using Simpson's rule as simp a, b, n. So I need to write a function called simp. A, b are the bounds of this integral. N is the number of partitions I have done to this bound. And then I finally print out the values of tint and exact I. Of course, we are going to need the function. The function can be easily calculated in this form, so I have written it out here. So you can see this is this function translated into Fortran. Now the main thing is about the Simpson rule function, and that's what I've written here. So here we start with these two numbers, t1, t2 are 0, and these are the summation terms. So these are going to be the summation terms here and here. And then I put h is b minus a by n. Now because this b minus a by n is coming at 3 different places, I just define it in one shot. And then I write two loops here. Later I'm going to simplify these loops, but let us for clarity now create a loop from k is 1 to n by 2 and a second loop from k is 1 to n by 2 minus 1. And here I have the term f a plus 2k minus 1 h. And here I have the term fa plus 2kh. So this is the first summation, this is the second summation here. And then I calculate the value which is given by the Simpson rule as h into fa plus fb plus 4 into t1 plus 2 into t2. Remember, 4 and 2 are the coefficients of this summation. And then I need to remember to divide this whole thing by 3 because this is the Simpson's 1/3 rule, and then I end the function. So what this function is going to do is that it's going to take a, b, n as inputs, and it's going to give me back the value of the integral I which has been obtained using the Simpson's rule. So here I have now coded this whole thing up and put it in the compiler which is on the web called onecompiler.com. Now of course you can download any Fortran compiler out there if you have access to some specific compiler like those by Intel or Nvidia. You can use that also, but I have simply taken this, I have copied and pasted the programs here, and then I have run it. So you can see that this program when run gives me some of these values. So here I changed some of these statements so that I can print Simpson and exact also. You can see the Simpson rule value and the exact value here. Now I printed out some of those summation terms here, so you can check with the summation terms I calculated by hand. Now one thing to remember here is that when I use n is 2, the second term here, this does not come into play at all, because this 2 by 2 minus 1 would simply be 0 here. So essentially there is nothing coming from this part. So this particular n is 2 does not check the algorithm in full. I could have some mistake here and I would not get that. So I'll need to do one more step here with n is 4. So this is pretty laborious, but I have gone ahead and done this using my calculator and so on. So I put n is 4 and then I take the formula, I put n is 4 here, and then I get all these values. Remember again, a is of course 0, b is pi by 2, and so I get this value of I. Now I need to find the function value at various points such as pi by 2, pi by 8, 3 pi by 8, pi by 4, and so on. And these have come from my expansion of these summations. So in this case what happens, k goes from 1 to 2, so there are going to be two terms here, and when I put k is 1, I'm simply going to get pi by 8, but when I put k is 2, I'm going to get 3 pi by 8. Similarly here I'm going to go from k is 1 to 1, so at least I'm going to get one term out of this here, and so that is simply going to be when k is 1, I will get pi by 4 here. Let us now take this value of I and calculate all the function values. So I calculated all the function values. Again, you know, f0 will be 1 by 4, f pi by 2 is 0, f pi by 4, f pi by 8, f3 pi by 8 can be calculated. These calculations can then be all put together in this particular formulation, and then let us try to see what we get. So I have done that in this particular slide, and you can see here these numbers are here. Again, I used all the decimal places which I have in my calculator, and so I got these terms here. Now again, remember this is T1 and this is T2 in my Fortran program, so I can verify these terms by the Fortran program to know if I have done this correctly. Now it could be the Fortran program is wrong or the calculator results are wrong, but when these two match, the feeling you get is a very satisfactory feeling. So that's something which is nice to know. So this is the final value of the I here, and I comes out to be 0.1576, which you know is pretty close or almost close to the actual solution. Now before proceeding further, I'm just going to clean up the code slightly. Now you guys all know that I was using these two do loops to calculate these two summations here. But you can clearly see that if I'm going from k is 1 to n by 2, then I do not need to go through that same path the second time. The only difference was that one case here is not being used, that is the n by 2 case. So I rewrote this code here in green. So you can see here that I calculate T1, and then I have this logic here that if k is not n by 2, then you calculate T2. So basically what you do is you go through this loop, but the only case you exclude is when k becomes equal to n by 2, which is the last point, which I do not need to consider when calculating T2 here. So this second summation is taken care of here, and I only have one do loop. I do not need to use two do loops. Let's put it all together in onecompiler.com, and so I have got this here. Now you can see here the do loop is combined into one do loop, and here I have now taken n is 4, and now I get these results out. Now if you go back and compare with the numerical values I obtained using my calculator, you will see that T1 and T2 are going to be the same here, and Simpson's rule is comparing quite well with the exact solution here. Of course, we are not happy with that comparison because it's not to all the decimal places. So what I did here is I put a loop on top of the call to the Simpson function. And so I go n is 2 to a large number 80 and I change its value in terms of 10. Let's try to see how this works out. So this is again in the same onecompiler.com. And this is the output I get. So you see here Simpson rule, as you will expect, as the number of values of n increases, the solution becomes very good, and here the solution is matching very closely, or at least to 8 decimal places here. So certainly we can be happy with that. Now if you go back to my lecture using trapezoidal rule and compare the two methods, you will see that this convergence is much faster than trapezoidal rule, but in fact there is the need of much less points as far as Simpson's rule is concerned. Now in most functions, the functions are actually quadratic in a local sense, so naturally Simpson's rule is going to do better than if you take a linear approximation, which was done in the trapezoidal rule. Now let's just take a look at how the function looks like. So again, I have taken help of Wolfram to do that. So I can actually plot the function here and I can see that it's pretty much a quadratic function. So no doubt it works out very well. So what happens here is that the integral value can be calculated using Wolfram and I get the number here. So again, I'm quite happy because now the solutions of different methods have matched, the one by the calculator, one by Fortran, and one by Wolfram Alpha also. So let us do some homework problem, or at least I can give you some homework problem. Try to write a double precision math code to implement this rule. Also look at the derivation. There are many sources out there on the internet where you have the derivation. Now the derivation is mostly laborious because you have to assume the quadratic and then you have to do a lot of algebra and simplification and so on. But at the end of the day, you are going to get the rule I have given in this video. Now there are a couple of questions you can think about. Now you can think about the question that if you wanted to do numerical integration, which rule would you use, trapezoidal or Simpson's rule? Now it may also be dependent on the function, so it's not a very simple case in all situations. So think about it, do some research on Google and maybe write your view on the comments. And also, are there more Simpson's rule? You will be surprised to know there are more. And so again, write in comment section about any rule you have discovered which we have not addressed in today's video. So in the last slide, I will just let you know the rule again. So this is something you can keep in your memory, or at least you know the form of this rule. So essentially you have FA plus FB, then you have a summation sign with 4 in front, and then you have the function values which you need to calculate at this point. And then you have one more summation with 2 in front and you need to calculate the function values at this point. So again, Simpson's rule is extremely good. It's extremely powerful for a large number of functions because, as most of you know from the analysis of function and also the way Taylor series works, is that most functions are well approximated using a quadratic function, at least locally. So even if you have quite a nonlinear function at a very local level, it's going to be quadratic. So as you keep increasing n, certainly the function is going to become a quadratic function at the small region where you are looking at the particular point of the function. So this was my take on the Simpson's rule, and I hope you enjoyed this video. Please share it with people you may know who want to learn Fortran or want to learn some aspects of numerical computation. You of course see that Fortran is extremely powerful. It's a language built for formula translation. And even though many more powerful languages have come up, such as Python and C++, Fortran actually is extremely speedy in terms of its implementation, and it's also very clear. And you will also see that its vectors matrices do not start from 0, which is a very big advantage.